Hello there guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we looked at the formula for the integral of a real valued function over a three-dimensional surface S, and we went through some sample problems to see how we use that formula. In this video, we are going to take a look at the integral of a vector field over a surface capital S. So as we would think, if we're going to talk about the integral of a vector field over a surface, we need a vector field, which we'll call capital F hat, and then we need some 3D surface capital S. This surface S can be parameterized by capital phi hat. When we have those two things, the integral of capital F hat over capital phi hat, or we could say the integral of capital F hat over S, is the double integral of F hat dot d capital S hat. Very, very careful there. That is a d capital S hat. And this is equal to the double integral over d of capital F hat dotted with the cross product of the vectors that are tangent to your surface. That's capital F hat dotted with the cross product of t sub u hat and t sub v hat. And this is the double integral over d, which is the domain of our parameterization capital phi hat. Now, just taking a look at the formula on the left here, just taking a look at that guy right there, without getting too much into what this is saying yet, just looking on the surface of this guy, and yes, that pun was intended, this formula looks very similar to something we've seen earlier on in the course. If you think back to when we first defined the integral of a vector field over a curve, either in R2 or in R3, we saw that the first statement and the first formulaic definition of the line integral was the integral over our curve capital C of capital F hat dot d little s hat. And if you just look at these guys side by side, very, very similar. So we will be doing some kinds of comparisons between the integral of a vector field over a curve and the integral of a vector field over a surface. Now, with integrals of vector fields over curves, we had two sort of main categories that we looked at. We looked at work and flow, and then we looked at flux. Because of the sort of dichotomy of curves in some sense, these were two fairly easy concepts to work with. Surfaces are a little bit more complicated, and we're only going to work with one of those two same types of things. One of them we sort of have to leave out. And later on in this video, we'll get to why that is the case. So another key part of integrals of vector fields over curves, one thing that we had to note was the orientation of our curve. We had to put some focus on the direction in which we were traveling on this curve. Based on the direction in which we were traveling, that would have a small impact on the answer. So we have to do the same thing with our surface capital S. We have to talk about the orientation of a surface. So an oriented surface is a two-sided surface. One side of this surface is specified as the outside, or the positive side, and the other side of the surface is called the inside, or the negative side. For every point that lies on this surface, there are two vectors that are normal to it, and these are vectors of length 1, so they're units, normal vectors. We can call these things n1 hat and n2 hat, and n1 hat is going to be the negative of n2 hat, and also vice versa. So each of these n1 and n2, they're each associated with one side of our surface. Now, a key thing here is that our surface has to have two sides. There are examples of surfaces that do not have two sides. There are surfaces that only have one side. For example, the Mobius strip. So the big question for us is, how do we find these normal vectors of length 1, and which one of these things do we want? So going back to earlier on in the course when we talked about vectors normal to a surface, we said that if we can parameterize our surface with capital phi hat, we can find the vectors that are tangent to the surface in the u direction and in the v direction. That's our t sub u and t sub v. If we take the cross product of those two vectors, that's going to get us a vector that is normal to the surface at the point where we're finding these vectors. So that is a vector that's normal, but it's not necessarily a vector that has norm or length 1. So if we want a vector that points in the same direction but has length 1, we're going to multiply every coordinate of this normal vector by 1 over the norm of that vector. So we have our parameterization, capital phi hat. S is a differentiable surface at every point in the domain of our parameterization. Then t sub u hat cross t sub v hat, all divided by the norm of that same vector, is something that we can talk about. It is indeed defined, and that is going to be the general formula for the unit normal vector to our surface at any point. Now, specifically just that guy, it will either be plus or minus. And based on which one it is, we have a special term for it. If t sub u cross t sub v divided by the norm of that guy is the positive n hat, then we say that the parameterization that we have is orientation preserving. But really what you need to know is that if your parameterization capital phi hat is orientation preserving, then that's that cross product vector, that t sub u hat cross t sub v hat, points to the outside or the positive side of our surface. If t sub u hat cross t sub v hat divided by the norm is minus the normal that we want, then it's orientation reversing. And that is to say that it's going to point to the inside of your surface. Now, the convention that we're going to use is that we're always going to use an orientation preserving parameterization. So that is to say, unless specified, we are always going to use the vector that is normal and points to the outside of our surface. So how do these unit vectors that are normal play into this formula up here? How is this going to help us change this guy right here into something that we've seen previously, and how can we work with this guy? So we're going to work with this guy right there, but we're going to make just a little bit of algebraic work with this, and we're going to see what this turns into. So you see that we start off with the double integral of d of f hat dotted with the cross product. I'm going to take this thing and I'm going to just multiply it by a big fancy 1. I'm going to multiply it on the top and bottom by the norm of that cross product vector. And I'm going to multiply that norm piece that's on the bottom. I'm going to multiply that onto the bottom of my cross product vector t sub u hat cross t sub v hat. Now that t sub u hat cross t sub v hat divided by the norm of t sub u hat cross t sub v hat, that is our unit normal vector. So we just make that substitution in there. So we're left with capital F hat dot n hat, my apologies, times the norm of the cross product. Well, thinking back to surface area, and when we talked about the differential of surface area, our d capital S hat, we said that d capital S hat was the absolute value or the norm of that cross product vector, the norm of t sub u hat cross t sub v hat. So we have the double integral over our surface, or the double integral over d, capital D, same thing, of capital F hat dot n hat ds. And what this is saying then is that the surface integral of a vector field over a surface is equal to the integral of the normal components of your vector field across the surface. Now, thinking back to integrals of vector fields over curves, we had our two special categories. We had work or flow, and then we had flux. Flux was when we took the integral of the normal component of our vector field across a curve, across a closed curve in the xy plane. So integral of the normal component of a vector field across a curve, integral of the normal component of a vector field across a surface. What this guy is talking about right here is this guy is talking about flux. What this is telling us is that this is telling us how do we calculate the flux of a vector field across a three-dimensional surface here. Now, one quick note on how does the parameterization and the orientation of our parameterization change the end result of the integral of a vector field across a surface? Very, very similar as to how the orientation impacts our integral over a vector field along a curve. If your parameterization is orientation reversing, then it's just going to multiply the end result of the orientation preserving parameterization by a -1. So orientation preserving parameterizations do not change the sign. If you reverse the orientation, then you are multiplying by a -1. So as we just said, the integral of the normal component of a vector field across a boundary should sound familiar. It's talking about flux. In the special case that your surface is the graph of a function of two variables, then the convention that we are going to work with is that the positive side of S is the side where the unit normal n hat has a positive k component. So the n hat will point upwards. We can come up with a very basic parameterization of our surface. In this case, capital phi hat is u comma v comma g of u comma v. And then we can find n hat without much trouble. We find that n hat is minus the partial of g with respect to x, or u, comma, minus the partial of g with respect to y, or v, comma 1, all divided by the norm of that vector. And then when you take this and you tune it into the formula that we arrived at, this is what it comes to over here. The double integral over d of f1 times the negative of the partial of g with respect to x, plus f2 times minus the partial of g with respect to y, plus f3. But really, what are the main forms of this formula that you are going to want to know and want to recognize? That guy right there. That guy right there. And that guy right there. Those are the three most common ways in which you will see the formula for flux in R3 written. So you should get comfortable with seeing these guys. So this was just a bit of a background into what the integral of a vector field over a surface is. In the next video, we are going to do some sample problems and see how we use this formula to calculate the flux of a three-dimensional vector field across a three-dimensional surface. If you have any questions or comments, be sure to leave them in the comments section below. Otherwise, until the next video, take it easy.